Bismillahirrahmanirrahim. Assalamu alaikum. I am Fakhr Lodhi and this is Formal Methods for Software Engineering, and today is our first lecture, lecture number 1. Now, what are formal methods? If you look at any dictionary, you will find out that formal means definite, orderly, or methodical. That means something which is definite, which is done with a discipline. That is what formal is. In software engineering or computer science, formal methods is a branch of both these disciplines, that is software engineering and computer science, in which we argue and analyze the computer programs using mathematical techniques and formal techniques. In formal methods in software engineering, these techniques are used to specify programs, not just to specify programs, that is to define the meaning of what this program is supposed to do, but also we will be talking about verification of these programs. That is, once the program is written, how do we prove that this program actually fulfills the specifications or the requirements of what this program was supposed to do. So this is specification as well as verification. Formal methods are also used for constructing programs. That is, we develop a program which is provably correct. That is, a program that is, we say that we write this program in a way that each step that we take in writing this program actually leads us towards the final solution, and we follow the methodology or a proper method through which we make sure that we do not take any wrong steps. So this is what formal methods is all about, and we will be talking about these different formal methods in more detail. There are a number of different techniques and tools available, and we shall be talking about those different tools and techniques in this course. Formal methods, the area started by the two most famous computer scientists, that is Dijkstra and Tony Hoare, and they have developed a lot of techniques and the methodology behind what we call formal methods today. These formal methods we will be talking about. We will be looking at what is known as Hoare's logic, which is basically the basic of all formal methods. That is, all formal methods, they are based upon the techniques developed by Tony Hoare and Edward Dijkstra. So these are the two main people. There have been many other people who have contributed in this field, and we shall be talking about those people in more detail. Now, the question arises, why should we develop formal techniques, or why should we study formal techniques? That is, what is wrong with what we already do? That is, if we can call it informal, what is wrong with that technique? Why should we at all have a formal technique? And this is what this course is all about, and we shall be talking about this in more detail, especially in today's lecture. If we look at the history of our software, the history of software has been full with what we call notorious bugs that have caused huge losses, financial as well as in terms of deaths, causing deaths to people. Okay, and there has been a long list of those kind of defects reported in the literature, and if you just look around, you will find many such defects that people have quoted in different books and different articles and so on and so forth. So I will just be talking about a few of them right now. The Byte magazine published a list of notorious bugs What are those notorious bugs? Let us look at a few of them. It is a long list of those bugs, but at this moment we will be talking about only a few of those bugs. So let us first look at that short list of those bugs. The first in our list is what is known as the Thirac25 bug, also known as the bug that killed. This is a bug that was reported in 1987, and in the last 2 years, that is from 85 to 87, there was a software problem in this machine which was supposed to give radiation treatment to cancer patients. And because of the software error, several deaths were caused because of that software error and over radiation. So the controller, which had a bug in its software, could not control the radiation, and it resulted in several deaths. So this is one example where the software error actually caused a number of deaths. And later on it was fixed, but the damage had already been done. The second bug in my list is the AT&T long distance breakdown. The AT&T long distance breakdown bug was reported in 1990. Actually, what happened was there was some ill-placed break statement in the code, and probably you have seen that in other examples also, especially in our software engineering course. The same example was quoted, but anyway, there was an ill-placed break statement in the code which caused this error, which caused the 1/3 of the entire American long-distance network to go down for more than 9 hours, and that caused huge losses, not just to the AT&T, but also to the banks and other credit companies which were using that network for their ATM machines and the credit card processing. So just one software bug resulted in a breakdown of more than 9 hours of long-distance AT&T network, causing huge millions of dollars of losses. The third problem in my list is also a very well-known Patriot missile problem, which was reported in the 1991 Gulf War. In this particular case, what happened was that this missile was actually supposed to hit an incoming Scud missile that an Iraqi army had launched. But instead of actually hitting the Scud missile, this came back and hit the troops, their own troops, the American troops who were sitting in barrack, and killing more than 28 people and injuring many more. So once again, a software defect that resulted in deaths of many people. So as you can see that these examples have shown that a software problem could cause a large loss in terms of lives and also in terms of financial losses. But there are many more examples. Another very famous example is what is the Pentium bug. This Pentium bug was, there was a software error in the microcode of the Pentium processor, which resulted in some miscalculations in its floating point arithmetic unit. So which resulted in Intel, they had to take this Pentium processor back, and that caused more than $400 million of loss to Intel company. And once again, a small software error caused a huge financial loss to the organization. So basically, the point here is that software is present in everywhere, in every thing that we are using today, from our microwave ovens to our cars to our computers, everywhere. And the use of these computers and the software which is actually governing that computer is going to expand. This will result in a lot of software that will be written. Now, what does that mean? That means a small software error could cause your microwave oven to actually explode, cause deaths within our households, and so on and so forth. So we have to be very, very careful when we write software for these kind of devices, where the system failure can cause a loss which is much more than the system itself. For example, if a life is lost, that means we are going to lose a lot just because of a software failure. So what can be done? This is what the topic of our discussion, and this is what formal methods are all about. Now, producing high quality software is what is desirable. This is what we want to do, because we don't want financial or loss of a life because of the software. How can we increase the quality of software? We have studied those techniques also, and some of those techniques include testing the software properly. Now the question is, can we properly test the software, or can we thoroughly test the software so that there are no bugs to be found later on when the program actually goes into execution? There is a famous saying by Dijkstra that you can only prove the presence of a defect by testing the system, but you cannot prove the absence of a defect. So that is, testing can only show if there is a bug present, but if testing does not show that there was no bug, or it does not uncover any of the defects in the software, that does not mean that there are no defects in the software. We all know this thing from our mathematical background. When we have a theorem to prove, all you have to do is you have to provide a counter example to disprove the theorem. That is, if we say that this is the theorem, all we have to show one example which does not fulfill the condition, and hence we say that this theorem is not correct. But on the other hand, you keep on giving examples of something, but that would not still prove that the theorem is correct. A very simple example is, that is, let us just assume that we say all numbers are less than 1000. This is our theorem. In order to prove this, we try to give examples, and we say 1 is less than 1000. That means the theorem holds. Then we say 2 is less than 1000, theorem holds. 10 is less than 1000, theorem holds. 50 is less than 1000, theorem holds. 100 is less than 1000, theorem holds, and so on and so forth. Now we have given several examples of numbers in which we have shown that all these numbers were less than 1000. So that means the theorem was holding, and the theorem was that all numbers are less than 1000. Giving those many examples, and in fact you can have infinite number of examples, because all negative numbers, they are going to be less than 1000. Therefore, you can have infinite number of examples that will show that all those numbers are less than 1000, but that does not mean all numbers are less than 1000. Now, that basically shows, this is just one very simple example. Maybe it looks trivial, it looks very silly kind of example, but it is a very simple example that simply shows that if you can show infinite number of examples, even then it is not possible. That does not mean that that proves a theorem. So what do we need to do? We need to actually prove the theorem using a formal proof of the theorem. If we can provide a formal proof, only then we say that the theorem is correct. Otherwise, we cannot say that the theorem is incorrect. So there are two things here. In order to show that the theorem is incorrect, you can either provide a formal proof of incorrectness, or you can provide a counter example. Both of these will work. But in the case that you want to prove that the theorem is correct, you can only do that if you show it with the help of formal proofs. Now, what does it have to do with testing and quality of code? Testing, as you know, when we write a test case is nothing but an example, a scenario that we run and execute, and we show the working of the program. Now, if one particular scenario works, that does not mean that all scenarios will work. Can you have all possible scenarios enumerated? Once again, it is not possible to have all possible examples and scenarios and test those scenarios using our standard testing techniques. What does that mean? Let us look at this very simple example. Now, let us look at this very simple requirement. We want to write a program to test for the quality of two strings. So given two strings, this program would tell whether the two strings are equal or not equal. So this is what the program is, and we have to write the test cases to test the program. So let us first look at the test cases. The name of the function is equal. It takes two strings as parameters, and so we write these different test cases. The first test case is equal. So we have the first string as the cat, the second string as the dog, and the expected outcome of this test case is false result. The second case is we have the same is equal function, and the two parameters, the first is testing and the second parameter is testing. That is, we give the same string and the expected outcome is true. Now we have a third case in which the two parameters are, the first parameter is house and the second parameter is home, and the expected outcome is false. So we can write many test cases just like that. I mean, we can have strings where we can have some numeric values. We can have strings where we can have some, non-numeric alpha characters, for example, special characters, and so on and so forth. We can have empty strings. We can have those kind of things. And we can test our program using all those different test cases. But would that actually help us? It may or it may not. It may find an error or it may not find an error. In fact, the three test cases that we have seen here, I'll show you in a minute the program or the code written for this is equal function, and then we shall analyze those three test cases and see whether those test cases actually give the right answer or not. That is, do they catch the problem or do they properly test the system or not? So here is our code, the sample code, and this code was actually written by a student in a class. There is a slight modification in this course that I have done, but this is an actual example of the code. Here is the body of the code. We have this equal is equal to strlen string 1 equal strlen string 2. So that is it is checking for the length of the two strings, and if the length of the two strings is equal, that means that we set the value of this equal, which is a Boolean variable, to be equal to true. If the length of these two strings is not equal, then the value of this equal Boolean variable would be set to false. So the next if statement, that is if equal, in this particular case this condition will be false, and hence we will come out of this without going into the for loop or the if statement and return the value which is the false value. So in that particular case we are done. That is, if the two strings are of different length, that means they are not equal, and hence we return an answer which is false. Now if the two strings have equal lengths, then this is what we do, that is we go inside the if statement, and inside this if statement we check the strings one character at a time. So this is the for loop, and this is how we are checking it. Now if you look at it carefully, if you pay attention, you will see that this code actually is incorrect. What it does, can you see it? When does the value of equal changes? If the value of equal is set with every iteration, and it is set either equal to true or false depending upon the ith character in both these strings. If the ith character is equal, that is in both these strings the ith character is the same, then this value will be equal to true, otherwise the value will be equal to false. So the value, if the value has been set to be equal to false, if the next character is true, that is if the next characters are equal, the value would again be set to true, and ultimately what happens is that it basically checks whether the last characters in the strings, that is the last character in both these strings, if they are unequal, then here the Boolean variable will be equal to false. If the last characters are equal, the value will be true, and hence we will only give the answer based upon the last character in this. And hence if there are two strings of equal length which differ otherwise but do not differ in the last character, that is if we have two different strings, for example house and mouse, these are two different strings, but since they do not differ in the last character, our program will give a true answer, that is it will give the result that both these strings they are equal. So basically you saw कि अगर हम कितने भी इसके टेस्ट केसेस लिख लें, that may not find the error. And in fact, if we analyze this program from a statistical point of view, and if we say that there were only 26 characters, there were no numeric characters, or there were no lowercase and uppercase kind of distinction, or there were no special characters, so we are just working with only 26 characters, then the probability of finding an error is 1/26. That is, coming up with a string or a set of strings where the strings are actually different but they have the same last character. So that means having the same last character, the probability is 1/26. That is 1 divided by the total number of characters that we are working with. So if we have n such cases, test cases, the probability of finding an error by those n test cases is 1 minus 25/26 raised to the power n. You see this number 1 minus 25/26 to the power n. 25/26 is a fraction. You raise it to any power, this number will still not be equal to 0. So finding the probability of this number, that is 1 minus this number, is still going to be more than 0. That is, from a statistical point of view, it is almost impossible. It is impossible theoretically to make sure that we give 100% satisfaction that we have checked this program to our satisfaction, and we are sure that there are not going to be any errors in this program. No number of test cases can assure you this thing. This same kind of phenomena can be seen with the help of structural testing. So far, the strings matching function, we were using what is the black box testing, what is called the black box testing. In structural testing, what we do is we look at the structure of the program. This structural testing is also called or known as the white box testing, where we actually look at the code, we look at the structure of the program, and we make what is called a flow graph, and then analyze the flow graph and look at, try to develop different test cases to test different components of that flow graph. What are those different components of the flow graph? Once again, just as a reminder, let's look at some of those components. Basically, there are 4 different components. That is, we have the sequence, we have the selection, and there are different types of selections. We have a simple if statement, we have if then else statement, we have the case statement, and then there is the loop. So we make the structure of a program using those 4 or 5 different structures and then analyze it. So let us first look at those 4 or 5 different structures and look at one example of a program of and its corresponding flow graph, and then we will talk about the limitations of testing when we do structural testing as well. So let us look at those notations. The first one here is a sequence. So sequence is represented by 2 nodes, an arrow taking you from one node to the other. So this flow graph is going to be a directed graph in which the nodes, they represent different components, and the arrows, they show you the path, that is the mechanism or the set of statements that can take you from one node to the other. So in the case of a simple if statement, which is our second component or flow graph notation, if the condition is true, we go to the intermediate node here. If the condition is false, we go directly to the outside of this if statement. So hence we have this kind of structure in our flow graph for a simple if statement. In the case of if then else statement, we have 2 paths. If the condition is true, we take one path. If the condition is false, we take another path, and each path has a non-empty set of statements, and hence we have a node there. So we have a node which represents the body of the if part and the body of the else part, and at the end, both of these, they join at the end of the if statement. And we have the case statement where we have the multiple paths. It is very, very similar to if else statement, and except that we have more than 2 paths here. Then finally we have the loop structure. The first node represents where the condition is, that if the condition is true, we go inside the body of the loop, otherwise we go out of the loop. And if we go inside the body of the loop, we execute the body of the loop, and then we come back to the first statement and test the condition again. And if the condition is true, we will go back again inside the body, otherwise we'll come out of the loop. So this is what the loop is. And here is a very simple kind of a program, a very well-known bubble sort program, and the corresponding flow graph. In this, I have marked different statements as number 1, 2, 3, 4, 5, 6, 7, and 8. And those are the points where a decision takes us. So, for example, we will enter into the while loop from 1 to 2. And this is where the condition is checked. That is, what is the value of this Boolean variable sorted. If it is false, we will come out of this while loop, and that will take us to statement number 8 or position number 8 in our program. There is no statement corresponding to position number 8. So otherwise we go inside the body of the loop, and that will ultimately take us into the for loop. And once again, there is this I is less than size, which basically is a check. If this check is false, then that will take us to the to outside the for loop and will take us to statement number 7, or the position number 7, which is the end of the while loop, which will take us back to the start of while loop, and we will check this condition for sorted again. And otherwise, if the condition in the for statement, that is I is less than size minus 1, is true, in that particular case we will go inside the for loop, and there we have the if statement, and if statement is structured using our if statement structure. This is a simple if statement with no else part here. So if the condition here is true at point number 4, we'll go to 5 and then we go to point number 6. Otherwise we go directly to point number 6, and that will take us back to the start of the for loop, and we'll check the condition again. So this is the flow graph for a simple bubble sort program. So what we do is we take our program, and using these simple components we make the flow graph for this kind of program. This flow graph helps us in understanding the structure of the program, and based upon the structure of the program we try to write test cases to test the different components of the flow graph and make sure that these different components have been tested. And so we try to ensure the quality or improve the quality or testify the quality, and but again there are certain kinds of limitations with this kind of testing. What are those limitations? If you remember, there are 3 types of tests that we can have, or 3 types of coverages that we can look for. So given a flow graph, given the structure of a program in terms of flow graph, we can have what is known as the statement coverage. The statement coverage basically means that we write a set of test cases, a suite of test cases, by which we execute each and every statement. So we make sure that at least every statement has been executed at least once. So that is what statement coverage is. So basic purpose of this thing is that all the statements in our program have been at least executed once, have been executed. That means no part of the system or no part of the program is there which has not been tested. So this is one level of coverage. The second level of coverage is known as the branch coverage. What is branch coverage? What we try here is that we identify different branches in our program, and we try to test all the branches. So we come up with a set of test cases which test all the branches. That is, we try that all different branches have been taken. So once again, that is the second level of coverage that we try to ensure. And finally, the third level of coverage is what is a path coverage. What is a path coverage means that what we try to do here is we try to execute all possible paths in our program from start to end. And if we can do that, that shows that there is no possible path which has not been tested, which has not been explored, and hence that is the only way that we can have to show that the program actually works. That is, if we can enumerate all possible paths in our program and then write test cases for those, then we will be able to handle that kind of situation. So these are the 3 basic purposes. The statement coverage is the lowest level of coverage, the branch coverage is the next higher level of coverage, and then the path coverage is the ultimate level of coverage. And that basically means that if we can have the path coverage, that means that we have enumerated, we have exhausted all possible permutations of the program, and hence we are sure that this program will actually work. But what is the problem? Why can't we have such a thing? That is, why can't we just have the statement, the path coverage? The path coverage, as we have already seen, is something which requires to enumerate all the paths and possibly write the test cases for all those different paths that are there. And hence, can we actually do it or not? let us look at it with the help of a very simple example. So let us go back to the flow graph of our very simple program and see how many different paths are required in that particular program. Here is a very simple flow graph in which we have a loop, a for loop, and inside the for loop there is an if then else condition. So nothing very complicated, very simple kind of program, the for statement and the if statement. So there are paths, for example, there is a path from 1 to 5. Other paths are, for example, we start from 1, we go to 2, we go to 4, we come back to 1, we go to 2, we come to 4, we come back to 1, and then we go to 5. This is one path. Another path could be we go to 1, we go to 2, we go to 4, we go to 1, we go to 3, we go to 4, we go to 1, we go to 2, we go to 4, we go to 1, and we go to 5. So this is yet another path. Now the question is, how many different paths are there? If you look at this program carefully, there are two possible branches. That means, every iteration we have two choices. We can either go to from 1 to 2 or from 1 to 3. So if we have n iterations, that means there are going to be 2 to power n different choices. That means each choice will present a path, because that will be a different path depending upon which choice did you take. I have given you a few examples earlier on. That means, for n iterations, there are going to be 2 to power n different paths. So if we have this n, the value of n to be equal to 10, we have 1024 paths. And if the value of n is 20, we are going to have over 1 million paths. So basically, we have seen that, for this kind of a very simple program in which there is only one if statement and there is a very simple for loop there, for the value of n to be equal to 20, that is, if this loop iterates 20 times, then there are over 1 million possible paths. Can you really test this kind of a program? Can you have 1 million different test cases to test all these different paths? The answer obviously is no. It is not going to be feasible to do that. And mind you that n is the value of n to be equal to 20 is a very small number. So we cannot have those many test cases even for those small values of n. And hence, we are back to the same situation, that is, we are not going to have these test cases where we can have the set of test cases which can actually show that the program in fact has no defects in it. It is defect free, it is error free, there are no bugs, and we can rely upon that program. So does that mean that we will have to live with the same kind of situation where we write a piece of software to control an atomic reactor, for example, and unfortunately we cannot test this software, and that results in one day some malfunctioning, some error condition which we did not check, and that condition resulted in this atomic reactor failure, its control not properly functioning or shutting the system down at time? Could we have a Chernobyl where there were the loss of thousands of lives? Could we have another Patriot missile kind of explosion? Could it be that software which is controlling an aircraft fails and the aircraft crashes? Those are very serious scenarios, scary scenarios, not just serious. Would you want to fly a plane in which you are not very sure about the quality of the software? Things can happen. Obviously, there is no guarantee anywhere in life, but one would want that we have the software which is reliable. In 1996, the Committee on Information Technology, the President's Information Technology Committee, presented a report to President Bill Clinton, which basically says that, we know how to write software which works for 95% of the time, but we don't know how to write software which works for 100% of the time, which is reliable. For these kind of systems where the software failure or the system failure, the loss of that kind of failure is much more than the system itself. We can lose human lives. We can have huge financial losses just because of some error in our software. So is 95% good enough? You fly your plane 100 times, and out of these 100 times, if it starts to crash 5 times, we are going to have a problem. So, what is the problem? What is the solution to this kind of problem? The solution to this kind of problem is what is formal methods. What we do in formal methods is we try to develop models of the system, just like we have models in our physics or chemistry or those other sciences. Here in computer science and software engineering, we also try to develop models, and with the help of those models, we will argue about the correctness of those models or those softwares using mathematical techniques, which are basically our formal logic techniques, the predicate calculus and the propositional calculus, and there are other things that we will be using. So this is what we will be looking at and we will be doing in our formal methods. That is, how to apply these formal techniques to, first of all, build the models and then argue about those models. Now, let us look at a model. What is a model, and why do we actually need a model, and how does this model actually help us? We will analyze this thing, we will look at this thing with the help of a game known as Dijkstra's game. This Dijkstra's game is presented to you with the help of these slides, and we are going to talk about this Dijkstra's game in a minute. So let us go back to the slides and have a look at Dijkstra's game, what this game is all about and what can we say about it. Now, this game is a very simple game. What we have is we have a jar full of white and black balls. Let's say we have W number of white balls and B is the number of black balls in the jar. Now, the game is very simple. What we do is we, reach inside the jar and we pull 2 balls back. Those 2 balls can be of the same color and they can be of the different color. So that is, the 2 balls could be one black and one white, or the 2 balls could be both white or both black. So these are the 3 possible combinations. Now the game is like this, that we have, if we pull back 2 balls which are of the same color, that is 2 white balls or 2 black balls, we put 1 black ball back into the jar. If the 2 balls are of different color, that is, one is white and other one is black, then we put the white ball back into the jar. So we pull 2 balls from the jar. From these 2, we simply look at the balls. If they are of the same color, we put a black ball back. If they are of different color, we put a white ball back. So it is possible that we keep pulling the white balls, so we have to put a black ball back into the jar. For that, let us assume that we have an infinite supply of black balls available. So we have a number of black balls available, so that when we pull the 2 white balls, we can put 1 black ball in. So this is a very simple game, a very simple rule, 2 rules. Now the question is, given that we have W number of white balls and B number of black balls inside the jar, and we play this game, first question is, does the game ever stop? And the game stops when we do not have a rule to apply. So this is the first question. And the answer to that question is very simple, the game will stop, because every time we pull two balls from the jar and put one back in, that means every time we are reducing the number of balls by one, and hence we will be ultimately left with only one ball, and since there is no rule for one ball, so the game will stop. So this is the answer to that question, is very simple. Now the second question is more interesting question. The question is, can you determine the color of the last ball? That is, given W white balls and B black balls in the jar, can you determine the color of the last ball? Let us play a few games so that you understand what this thing is all about. Let us start with only one ball in the jar. So if there is only one ball, this could be black or white, and since there is no rule to apply, there is the last ball in the jar, and hence that is what the color of the last ball is. So one ball game is a very simple game. Let us play two ball game. With two balls, we have there are three possible combinations, both white, both black balls, one white and one black. So we pull one back from the pair from the jar, and both of these, if they are of different color, that is one black and one white, we will put the white ball back, so that is the color of the last ball. If both of these, they are of the same color, that is, we had two white balls and two black balls, we will put the black ball in, and that will be the color of the last ball. So you can play any number of games. You can have a 3-ball game, 4-ball game, and so on and so forth. Now the question is, once again, what is the color of the last ball, given that we have W white balls and B black balls? Can you determine the answer? I'm not going to talk about the answer in this lecture. Think about this question, work on that question, and we'll discuss this problem in our next lecture. That is, and then we will see how these formal methods and formal techniques and the models that we build using these formal techniques can help in arguing about a certain outcome and help us in understanding and analyzing the system. So kindly look at this example and work on this example so that let's see if you can find the answer and can come up with the color of the last ball that is there. मैं इंशाल्लाह अगले lecture में we will discuss it in the class and in the lecture and give you the answer and show you how to do it, but try to do it yourself also. So wrapping up, what are formal methods and why do we need formal methods? We saw that software is everywhere and it is controlling very critical systems. It is controlling our financial institutions. It is controlling embedded devices. It is controlling some very critical devices such as cruise missiles, the aircrafts and the atomic reactors and so on and so forth. And it is used in health sciences and used in all kinds of industries, and a small problem in the software can cause huge losses, huge damages, and that can also result in loss of life. So not just financial losses, but also lives are at risk. So what we need is, we need reliable systems. We need systems that work. We do not need systems that work for 95% of the time. We need systems that work for 100% of the time, and they are reliable like other systems that we have, for example, in our other engineering and sciences disciplines, the bridges and the machines and so on and so forth. So for this we need formal methods. Inshallah, we will be discussing that in the next lecture. Until then, Khuda Hafiz and Assalamu Alaikum.